Good morning and welcome to this training session of the PeneloPe project. The title of the presentation is Fundamentals of Automation ML. I am Roberto Raffaeli and I'm an associate professor at the University of Modena and Reggio Emilia, which is one of the partners of the PeneloPe project. I am a mechanical engineer. My background includes some knowledge about software coding, geometry representation, and algorithms to process geometry. My interests include the Industry 4.0. In detail, my major interests are in industrial robotics application, for instance, VAM applications, digital twins, and augmented reality applied to new phases of the product development, such as inspection activities. I am part of the XLab, X and the Loop Simulation Lab. The lab deals with Industry 4.0 activities and splits in two major topics, which are the research of human-centered design, virtual and augmented reality, and user interaction. And we have a second would say core of our labs, which is devoted to automation, industrial robotics, and human-robot collaboration. Both these major topics of our labs has been involved in the PeneloPe project. What we have done in PeneloPe project, basically we concentrated on a few topics, which are the assessment and compensation of positioning errors of industrial robots in extended workspaces. We tackled also the monitoring on the human workload in virtual environments, workload physical and ergonomic, physical and cognitive workload of operators while doing manufacturing tasks. And we also worked on virtual commissioning tools and their integration with the PeneloPe digital thread. So what's about the training session of today? Basically, the goal is to focus on automation ML. Automation ML is a modeling language. So what we want to do is to provide a basic understanding of this language, its goal, its main applications, which have been developed in the industry, and above all, the usage we have done of automation ML in the PeneloPe project and in the pilot line where it has been experimented, which is the Fokker Aerospace pilot line. So a short summary of the presentation of the talk I will give. We will speak about some general concept about automation ML. We provide some examples, starting from the early examples of usage of automation ML. And then we will present an application, a software application we are developing in our lab, which is called Automation ML Hub. Its main structure, the main goals and achievement we have reached so far. And then we will focus on the PeneloPe project and how ML has been used to link the physical and control assets of the Fokker pilot line to the digital thread. So let's start with the general concept about the automation ML. Automation ML is basically a modeling language. It's a neutral data format which is based on the well-known XML format. And the main aim of automation ML is to store and exchange data between, or would say inside, automation systems. So the idea is to have a tool to allow the interconnection and then the exchange of data between very heterogeneous tools that we have in modern landscapes made of several engineering tools in automation systems. So we have the mechanical part, we have the electrical part, the control PLC systems. So very heterogeneous set of tools that need very different ways of very different types of data to be exchanged. So the idea, as we may see on the right, is to extend the use automation ML along the different phases and different steps of data exchange, moving from CAD systems to CAE systems until process planning and manufacturing stage. And the usage of automation ML also extend to different scopes of the process. So we not only include data about the product, which usually are conveyed through geometrical representation, but we also extend to the process, take into account, for instance, the logics, the phases of production, and we also take into account the description of the resources we need to accomplish a certain production process. And as we can see here, we usually concentrate on discrete production system, but also continuous production could be taken into account. And here on the left side, we see that we have many scopes that are included or are targeted by the automation ML, including documentation, motion, control logic, geometrical description, and so on. So automation ML has today a quite long history. It was founded, the idea of automation ML goes back for more than 10 years ago. And the idea started from few companies and research entities that wanted to provide a data exchange format to cover the needs of data storage and exchange in production system engineering. And the idea was, as said before, to find a tool that was able to integrate heterogeneous tools. We have standards in many fields of engineering. For instance, let's think about geometric representation, but there the exchange is almost between includes the geometry of a certain product, and usually the geometry exchanged between geometry representation kernels that are very similar one another. While in automation we have a very different domain of knowledge, so we need something different. Today, the association of companies that are researching or using automation ML has been expanded. There's an association putting the members together, and this association does a very good job in providing application guidelines, providing white papers, examples of applications, and keep on with the definition of your standards and extension of the language. The research on automation ML concentrated mainly on special engineering information, that is, to cover special domains of knowledge, for instance, the configuration of automation device networks, or how to model new production processes, or extending to new process that may appear on the market. And the second direction is the data exchange scenarios. Here the focus is how to use automation ML to exchange the data between different systems, including the way to transmit the information, for instance, using other standards that, for instance, the OPC UA exchange format. Here in the slides, we found some of the names of the logos of the companies taking part of ML Association. How we may see, there are many companies involved with automation, providing solution ranging from software application, PLC, hardware devices providers, or end users. One can be part of this association. There are some fees. I have reported them in the slide to become part of the association. And of course, email is an open standard, so everyone is allowed to use AutomationML, but being part of the association can give some advantages that are of course, the possibility to take part to new developments and extensions of the language. One of the major topics related with AutomationML is semantics. If we have two different tools and we need to exchange data between these tools, so we have a sending tool where some data are generated, and then we have a receiving tool. It's another software, another system that needs the data exported from the previous system. The hardest part, the most meaningful part of the exchange process is to have a semantics used to convey data from the first tool to the second one. What I mean is that the receiving tools need to understand data from the sending tool. It needs to use a common semantics to understand, provide a meaning to the data which are exchanged. One of the main focus of AutomationML is to give the possibility of using flexible semantics or to include semantics inside the data flow itself. These characteristics of AutomationML make it very useful and interesting in the Industry 4.0 ecosystems. We all know about RAMI 4.0 framework. RAMI 4.0 is a way of standardizing data flow, information flow inside Industry 4.0 environments, and it provides a sort of reference for manufacturers, developers, integrators in developing solutions. REMI 4.0 has identified the Industry 4.0 systems made of classified on different directions, on different dimensions. We have several layers. We are going from the physical assets until functional and business layers. We have different levels in the hierarchy of the systems, and we have different stages along the life cycle of a product or a systems. In this ecosystems, complex ecosystem, AutomationML providing a semantics-based exchange data system, it's very useful as a tool to exchange data in flexible manner. So how we may see here in the picture, it's very horizontal way to support the flow of data among the different dimensions of a Industry 4.0 system. So how we can conclude the definition of AutomationML? We can spend a few words about its motivation and scope again. So the focus on data flow along the entire life cycle of a production system. We have spoken about the heterogeneity of data along the production systems, where data are generated in different formats and different stages of the process. That include the generation of engineering data from the design phase, but extend until the physical realization of the system. So AutomationML wants to support also the data regarding the commissioning, the put in place of a certain production system, and wants to support also the operating phase of a certain systems. So as we may see from this scheme, there are many phases of the product life cycle which are targeted by AutomationML. Of course, not there are few others activities that are out of the scope of AutomationML, for instance, marketing, sales, or other accessory phases connecting with the production that are not in the scope of AutomationML. But for sure, AutomationML has a strong focus on supporting the digitalization of processes, so the possibility of getting rid of paper interfaces, or would say unstructured interfaces. In this slide, I have collected a few links that may be useful as documentation or reference in introducing AutomationML. I'll go through them very quickly. We may start with the very first one, which is the AutomationML page on Wikipedia. And as you say, here you find just a basic definition of automation ML, but it contains few other links that could be useful as an entry point for sure. And then maybe the most significant source of information is the Automation ML web page. Here you find a very exhaustive site where you find definition about automation ML, motivation, and also a few of the material I used for this presentation. You have a link to the tools that may be used to produce or reading automation ML files. You find some information about some books, publications, papers that are useful to have an understanding of automation ML, and you have some reference about the automation ML organization, who is part of this organization, but also example of industrial application. Here is under construction, but here you have some examples of usage of automation ML files, some news, a download section. So I think very well done work, and making this site very useful to understand how to use automation ML. And then for those of you that are more interested in coding issues, and so who wants to have an understanding how to read and write automation ML in software applications, I would suggest this page. It's a GitHub repository where you have some links to some libraries, softwares, such as the ML engine we will speak about in a few minutes, or automation ML editor, or a link to the page, to the code or repository where you can find how to build plugins for automation ML editor. So this, I would say, it's another very useful page to make use of automation ML. And also, remaining on the side of programming, this page contains the NuGet package to download and use to make plugins for automation ML editor software. But I put here also additional links to other topics that are strictly related with automation ML, starting from the standard, which is used to write an automation ML file, which is the International Electrotechnical Commission IEC 62714, which contains the format definition of AutomationML. It's a standard, so it's sold on the web store of the IEC website. And this standard is made of 5 parts. So basically, if you need to have an overall view on the standard, you need all these standards. But I can assure that using the material on the AutomationML website, you can read in the material provided there, so the white papers and examples of usage, you will find enough material for a quite broad understanding of AutomationML. And there are other referred standards in AutomationML. If you are interested in geometric aspects, we will see that Collada format is used to convey geometries. So I put here the link to the Chronos web page where you find the definition of the Collada standard, its formats 1.4 and 1.5, and you have linkages also to specification software tool to read and write Collada. It's a quite specific topic, but it's useful if you need to convey geometries using AutomationML file. And finally, sometimes the SDF format, simulation description format, is also referred in AutomationML file, and in this case, this is the page where you find the definition of this standard, which is used to convey simulation environment, robotic representation in virtual environments. I think that all these links together provide a very nice overview and very complete overview on AutomationML. So now we can have a closer look to the AutomationML file, how it looks like. I may start from this standard that provide a format which is called CAEX format, CAEX format, which is not a new standard. This standard was taken as a way to build the XML file of the AutomationML file. So here I'll put in the slide this preview of a file, and you see from the very first line of the file that basically the root node of the XML is a CAEX file. So that standard was taken as a reference to build the structure of the AutomationML. AutomationML basically is a tree. It has any XML file. So we have an hierarchy of objects. These objects are called internal elements, and we can build quite freely this structure. And not all the information is stored inside a single ML file, but the commission who decided the format of ML file made a very clever thing. They decided to use other standards which are very similar in structures and also in the concept of AutomationML, uses very similar way of structuring the information, and they decided not to replicate the information that could be conveyed by those similar standards. I'm referring, for instance, to geometry. Collada, as I've seen from the website I showed you before, was a standard conceived to convey geometrical data in XML format. Not only geometry, but also kinematic information, so joints, for instance, that are very common and I would say fundamental in automation systems. And the idea of Collada was very similar to AutomationML. So the decision was to use Collada to convey this information as an external reference of a certain AutomationML file. The same was done to represent production processes, behaviors, sequences that are commonly found in PLC coding. In this case, a standard called PLC Open XML exists to convey this kind of information and to represent the code, the structures contained in PLC programs. And the idea here was not to replicate this information again in the new ML standard, but simply refer to an external PLC Open XML file. And maybe in the future, other standards could be included and referenced by an XML, an automation KAIX XML file. I would like to spend a few additional words about the KAIX format. The KAIX format was defined in the IEC standard 62424, and it was defined to represent the P&I diagrams. So we are speaking about industrial plants. And again, the idea was to exchange data between different P&I tools. And the KAIX format has different versions. And the version that appears and as used in AutomationML files are the 2.15 and the 3.0 revision that are both supported in automation in an AutomationML file. And the most significant contribution of the KAIX format is that every element of the hierarchy of objects called internal elements that a certain NML file is made of, it's connected, of course, it's a son of an instance of the instance hierarchy root node, but has some attributes, interfaces, some reference to role classes and system unit classes. These elements I have mentioned are key elements of an AutomationML file and are the means to convey the semantics of a certain element of the AutomationML file. Just to give you a feeling, we have of course, the instance hierarchy that we may say it's the root node of all the hierarchy of objects inside the file. But every element has a certain role. Role is the specification of the type of object which is represented by the internal element. So for those of you who has a coding background, I may say that the internal element is an object, while the role class is the class the object is an instance of. So it's the same relations we have in class basis, in object-oriented programming languages. In object-oriented programming languages, we have the concept of class and object. Here we have the concept of role class and internal element. It's quite the same concept. So it's a way to provide a semantic to a certain internal element. We will see that we may have more roles for a certain internal element in AutomationML file. And then for instance, here we see in automation system, we may have the role to be a sensor or an actuator and a transport system and so on. But here in AutomationML, we have also the system unit class. What is the system unit class? It's a specific type, vendor-specific type of object. So if the role is, for instance, to be a robot, the system unit class may be a certain model of KUKA robot. So a specific type available on the market or clearly defined type of object. And these concepts rise to represent and to store certain types of object in a reusable manner. So the concept of system unit is born to provide the means to have reusable objects to be taken and used once they have been defined and stored in a certain library. And then we have interfaces. The concept of interface, it's I think quite straightforward. It's the interconnection between different objects. So we have this tool to represent a connection, for instance, an energy transmissions, mechanical connection, and so on between objects represented in AutomationML. And finally, we have the concept of attributes. Attributes are properties, specifications of a certain object. For instance, a power, a length, a certain characteristic of an element. So in order to summarize how semantics is represented in an AutomationML file, we have found that the objects are represented by internal elements that are organized in a tree of objects. So it's very similar to a CAD-based representation, for instance, in an assembly file of a CAD system. And each element refers to few classes, role classes. This reference appears in a twofold manner through the role requirements and the supported role class, but basically both these references are to role classes, so basically they convey the same meanings. Then we have references to system unit classes. If we want to provide a more specific reference to a vendor specific, to the very specific instance of object, we have the system unit class concept. And then we have other reference through the attributes. For instance, we may use the ref semantic attribute to additional references to the semantics. So we have quite few ways to make a specification to the semantics of a certain object. And in general, the AutomationML file is a quite complex structure in which we have a different section. We have mentioned the instance hierarchy, but we have also other sections into the files. We have any header, where very standard header information are conveyed about the author, the generating systems of the file. And then we have the instance hierarchy section, but we have also some libraries, because the idea of AutomationML is to be self-contained. So the semantics, the definition of the semantics is to be included inside the file. This is the way to give to the receiving software tool of the AutomationML file the key, the way to understand what is the meaning of a certain node in the file. So no external reference, but all the semantics that it is needed, it's included inside the file itself. And this semantics is organized in some libraries, which are the libraries containing the role classes we have defined, the system unit that we have defined, and also the interfaces we have defined. That since we may have also custom defined interfaces. And as you can see here, the roles or the system units or the interfaces may be organized as trees as well. So we can have also a sort of hierarchy and a sort of organization inside the library themselves. And as you see here, each node has some external references that can be used to link the objects together, and usually this is done by interfaces. Or we may have external reference to external data. for instance, to a geometry representation in collada format. You see here this extension, die extension. This is, die is the extension of a collada file, or we may have reference to external XML file, for instance, a PLC open XML file. This is the way and the network of connection we may have to represent an automation system through AutomationML format. To summarize the way the semantics is conveyed and the standards being integrated in AutomationML definition, in this slide I made a sort of bullet list of the main elements of an AutomationML file, which is divided in a description of the component topology, so the hierarchy of object, and a network of information which includes the properties, the attributes of the single objects, but also connection interfaces between the objects as described by the KIX format. And then we have references to the description of the geometry and the kinematic of an object, and this is done by the collada format. We have a description of the logic data, the control, describe the system control data, and this is done by the PLC open XML format, so again an external reference. And then finally we have all the relation among the AutomationML objects in terms of hierarchy of objects, but also free linkages among the entities that one wants to instantiate. But how to write or read AutomationML file or integrate these files in automation systems? Basically, the AutomationML associations provides two tools. The first one is the AutomationML editor, which is a Windows-based software for viewing and reviewing or creating or modifying AutomationML files. This software is provided with a free license in its basic form, which has some limitations. For instance, you cannot save objects beyond a certain dimensions, files beyond a certain dimensions, or you cannot add plugins to the AutomationML editor. Or if you want, you can buy a license to extend the system to its full functionalities. The AutomationML editor is currently under development, so new releases are periodically found on the website of the organization itself. We have also a second tool which is provided by the association, which is called ML Engine. ML engines basically are libraries, software libraries, based on the .NET framework, so they are written in C#, and they can be used to write your own code, your own software, and they can be integrated in your software to provide the capability to read or write AutomationML. Let's have a closer look to the AutomationML editor. As said before, it has been conceived to visualize the measure AutomationML concept. I would say that more or less it includes all the concept we may found in the specification of the language and books or white papers that we are on the website of AutomationML file, or also included in the KIX format. However, we have to say that AutomationML editor is mostly suited for educational purpose or as an entry point for who is learning AutomationML or is experimenting and trying to understand AutomationML, since there are few possibilities offered by the language which are not included in the software. And well, here just a list of its main features provided by AutomationML organization, distributed under the MIT license model. It includes, as said before, the major characteristic of the language, and it supports both the KICS standards that in terms of AutomationML are numbered as 2.0 and 2.10 format, respectively, for the KICS 2.15 and 3.0 release. And how does the AutomationML editor looks like? It's made of some windows. We have 4 for the preview for the first 2.0 standard and 5 for the new standards. In this slide, we have an example of an application of usage of the ML editor software. In particular, here, the representation is related to the XLab, the UNIMORE XLab lab robotic cell. And here we have used ML to represent our experiments related to the increase of the accuracy of the positioning accuracy of the Kuka robot system we have in our labs, thanks to the feedback provided by a laser tracker. So we have here in the first window the structure of our system, which is composed that the description of the equipment. So we have a robot, the robot is mounted on a slider, we have the laser tracker, we have a Wendell tool that we have used as a payload for our robot. But we have also the definition of the process. So we have defined a linear path to be accomplished from a certain starting point to an end point. And we have also a process control system that is represented by an algorithm which is used to compensate the positioning error. And as you may see, this hierarchy is attributed with some roles. So, for instance, the robot behaves to the robot role class. So, down here we have a library of UNIMORE role classes. In this class, we have the definition of abstract entity roles. So we have the robot role class, we have the robot sensor interface, we have the laser tracker role class. So we have the definition of the basic elements in an abstract way. In this window here, we have the system unit classes. So the abstract definitions here becomes definition of predefined and reusable blocks. So we have the specific definition of our Kuka robot, which is highlighted here, and on the right hand side we can see the attributes of the specific robot. So our robot has a payload of 210 kilos, a reach of 2,700 millimeters, the type of a robot is specified, the vendor, and so on. So those are attributes with specific values that are part of the specific system unit class. And the same for the specific Faro laser tracking system or the compensation algorithm provided by K-loops. And in the hierarchy object, you see that you can specify the abstract role, but also the specific system unit class, which is referred by a specific node of the hierarchy of objects. Finally, we have also a library of interfaces that may be used to connect, for instance, the algorithm to the tracker or the system who's running the specific algorithm. And in the new release, the 2.15 version AutomationML, also personalized attribute can be defined and they are available in a specific library of attributes. Since the scope of AutomationML is quite broad, files can become very big. So the information could be split among several AutomationML files. And as mentioned before, we normally used external reference for geometry, PLC open files, and so on. So the ML provide a mechanism called the AutomationML container to make distributed files. The information is distributed among several files, which are then put together in packages, sort of zip files, which has an extension AMLX to be distinguished from standard ML files. And the standard applied is the Open Packaging Convention, OPC. And we need also to say that the reference of an AutomationML file is to other AutomationML, could be to CAD or other files such as PDF, for instance, could be to OpenPLC files. And the reference could be self-contained. I mean that the containers, the reference file is inside the container itself, or could be also to reference outside the container to some public repository. And in this case, we may use links with the URI syntax to any public document which is available in the network. So the structure of the container is quite complex. Could be the root ML file acting as entry point, could be a library of ML files, could be a Collada file, PLC open file, but any other content that we want to put and add to other repository to complete the information. And here is described the process of designing an AutomationML file, which is not that easy task, I would say, or at least it needs to be done with a series of activity. So we need to start from the definition of the classes, the roles we need to represent all the elements we have in our we want to add in our software. So we have to develop these role classes or specific attributes for the classes. Then we can pass to the development of the system unit classes, because these abstract definitions becomes specific definitions for the specific instances we have in our file. And then we can integrate all this system, creating the actual ML file we need, and then we have to think also how to exchange the file and to integrate it in our system. And finally, I would like to recall the fact that there are many domains which are relevant for AutomationML file. As we moved today from the fact for the general goal of the AutomationML, which is to glue together data information regarding automation system. So now you can understand from the information provided so far that there are several scope in the system. So we have the electronical engineering, the mechanical engineering, so the geometry and the kinematic of our system, but we may have also the coding activity, the logic, the programming, but we may use also AutomationML to convey information about plant planning, about the simulation of the single step or the whole system. We can use AutomationML to convey documentation by means of external links or embedded files of our system. We can use AutomationML to describe HMI of our systems, automation systems, or to monitor the systems to gather data about the usage of the system, or the processing data in the system, and so on. So as you see here, very broad scope, and that means that the spectrum of application is very wide. That means that there are many stakeholders which are involved in automation ML, with automation ML. Of course, we have already encountered the association, which basically has the task to define the standard and maintain and expand the standard. We have understood that in automation ML we have the way to define system unit class. That means we can have packages of description of systems. So also vendors of automation system, or for instance automation devices, maybe you may use automation ML to represent their device, to convey all the information connected with such devices. But of course, then we have the usage, level. So we may have an application supplier or system integrator, which can use automation ML as a way to bring information along the system. Or we can have operator that use automation ML to store data about the usage of the system. We can use automation ML to track the maintenance of the system, and so on. So as we anticipated at the very beginning of this presentation, the use of automation ML goes through the several steps of the process. I would like to conclude this part of the general concepts of automation ML, going into detail about the collada file, the collada formats, which is used as written on the title to represent the geometry and the kinematics of an automation system in automation ML file. Here on the right, you have an example of a collada file. You can see, I think, that the first thing to be noticed that it's very similar to automation ML file. In fact, it was chosen because the concept and the way of building the file is very similar between the two formats. And what is the content of collada file? Basically, we have the representation of the geometry and as meshes, so as a list of triangles. The geometry is represented by the solids are represented by their skin, and the skin is made of a set of triangles, basically. But we have also the definition of materials intended of appearance of such as color or reflective properties of the appearance of the material, lights, camera with visual scenes. And then we have also the addition of the kinematic model, so how two parts can slide one on another, or how a joint can rotate. This is the information that is commonly used and in a system for the virtual prototyping of automation system, such as, for instance, the systems for online programming, less RoboDK or ABB RoboStudio, as in the example I reported in the slide. And a very important point is the fact that in collada we have the usage of IDs for each object. So you can see here you have an effect with ID 1, and then we have a material with ID 2. Every element in the file has a unique ID. And this concept is important because such ID can be used by an automation ML file, which is an external entity respect to the collada file, to refer internal elements of the file, of the collada file. So the presence of the IDs which is guaranteed also in an AutomationML file, it's very important to instantiate cross-links between elements of separate files. And it's a key element of the concept of automation file and of the referenced files. Collada has two main versions. The first one is 1.4, which is a stable release that supports geometry, meshing, morphing, animation, also shader, which are pieces of codes that are used to render scenes in extended reality applications. There is also a new standard called 1.5, which extends the functionalities of Collada. For instance, it includes the kinematic representation, geometry provided as a solid birette format, so in a format which is similar, which is homogeneous with the representation of the shapes in a mechanical CAD system. However, I would say that Collada 1.5 is not so supported at the moment among the several tools software tools we may find in engineering applications. In this slide, I have reported the mechanism used by an AutomationML file to reference an external Collada file. In the AutomationML files, we have the external data connector. It's a basic abstract interface that can be used in general to link external files. This interface class has a subclass, a derived class called Collada interface, which is used to reference the specific Collada documents. So you can see here it's just a piece of AutomationML file here, and you see that a certain internal element named geometry has an external interface named Collada, whose role, ref-based class path, is external data collector / Collada interface. Is of the type Collada interface. And then inside this external interface, we may find some attributes. We will see them in a while, containing, for instance, the URI, the reference, the path of the file which is referenced, and other information. And as an additional specification of the semantics, we add to this internal element named geometry a certain role requirement, which is to be a Collada geometry attachment, which is an additional information providing the fact that the node is a link to a certain geometry. And another important concept related to the fact that an ML file may link several elements, may have several internal elements with the geometry associated to, is the fact that we may need to position such geometry each other in the whole system represented by the AutomationML file. And that is accomplished by the attribute named frame. Frame is then usable to specify the position of several internal elements, each containing the reference to an external geometry. And basically, the frame is a specification of relative translation and rotation of the node in the system represented by the parent internal element. So as in assembly CAD system, we can make an hierarchy of elements which relative position of each child element against the parent element. And finally, as we have seen from the previous slide, each Collada interface has some attributes. So under the node representing the external interface, we have some attributes. And here we may have three options. The first one is the URI, so the universal reference to a certain path where we can find the die file, which can be a relative path compared to the, of course, the ML file itself, as in the example, but we may also use an external reference to a web domain, for instance, like in the web. So it's a quite flexible way of referencing files. Then we have another attribute called the type, which provide to the collada a character to be explicit or implicit. Or we may have also another optional attribute, which is the target. And this one is used to reference specific IDs, so specific elements inside a certain external geometry. So we may refer to specific geometric elements inside a collada file. Here I have reported some references about examples of libraries or coding projects that have to write or read collada files. The links you can find here are different libraries or tentative at different levels of development, but I think they can be useful if someone wants to try to read or write a collada file, which I would say it not an easy task because the standard is quite wide and there are many elements to be written or read from the file. So, and we also have two different standards, so it's not that easy. And of course, there are authoring applications for Collada. You can export or import Collada file from applications of commercial application on the market. But I would say that the landscape is quite heterogeneous. If you have a look here in this picture, which I have taken from the website of Collada itself, you see that there are applications able to deal with the Collada file, which are Maya or 3ds Max, so rendering applications, or SketchUp, or Unity itself, which is the well-known engine to develop gaming application or virtual reality, extended reality application, or Blender itself. But you don't see, for instance, mechanical CAD systems. To tell the truth, there is an emerging standard, quite new standard called GLTF. TF stands for transmission format, so it's a graphic language transmission format. And it's a new standard of the Kronos consortium, so the same that defined Collada, which has more modern features. For instance, can be compressed, the file can be compressed, can be provided in binary format, and it gives the possibility of using the file for real-time application. So it's a way of extending the capability of Collada also to more modern application environments. However, I've done a small research on the possibility of import and export of Collada and ML as a whole format in some of the applications you may use in your automation robotics application. I must tell that it's not a complete survey, so please take it as it is. But just few observations. The first one is that traditional CAD system such as SolidWorks, Solid Edge, Fusion 360 do not provide means to import or export collada, and I think this is a strong limitation, or at least it requires intermediate system to generate a collada file. For instance, you can use Rhino Zeros or OnShape to export collada. The second observation is that the majority of the systems uses collada in the format 1.4, while in automation application we need 1.5 format to convey kinematic information, joins information, and this is another limitation, I would say. And finally, we can see that ML is not supported at the moment in the majority of the system, the engineering tool we may use, since AutomationML has been implemented, but it's used in systems such as PLC authoring tools, for instance, TwinCut, but there the ML conveys information, for instance, as signals mapping, so very specific information, or you need to use the PLC open format directly to convey the code of the PLC, but there is no way to have an already predefined ML file, so just a PLC open file. Or there are other few systems able to convey ML files, such as the TIA system of Siemens. So another platform devoted to PLC and logic definition. Or we have AutomationML in the exchange process between Eplan and PLC systems, so exchange of data between electric engineering and electrical CAD. So once again, ML it's lacks, especially where geometry of the system is needed. Now that the basic concept on AutomationML has been provided, we can move to some example of application, just to clarify how AutomationML can be employed in actual Industry 4.0 scenarios, and what are the steps to implement such a system. I would start recalling one of the basic concepts of automation ML. Let's say we have two systems and we want to migrate some information, for instance, from a PLC system. So Emily here is using a PLC system where she generates some information, for instance, signal mapping, and then we want to recover this information in our robotic system simulation. For instance, as here in the figure, we have a ABB RoboStudio application used by Lisa. And of course, we know that in ABB RoboStudio, we need to map signals which are exchanged by the controller of the robotic cell, for instance, a PLC system. So it may be useful to have the migration of this information from Emily to Lisa. And we can do it in many ways. For instance, we can just list the signals in an Excel file and then recover and input the signals in a RoboStudio. However, this is a very manual process. We have no tracking of our activity if we need to change, or Emily would say needs to change some signal, and of course it's not well supported process. And AutomationML, as said before, comes in our app in this kind of scenarios primarily. And the idea is to provide a format able to convey and exchange several types of information among different users and different authoring systems. And the mechanism is quite straightforward. We have the source tool, so in this case could be the PLC system, and then we need an exporter of the information in AutomationML format. So this neutral data model needs to be imported in RoboStudio in the target tool and used to automatically complete the information which is conveyed by the file itself. And why have recorded this basic path of information? Because when we export information and we use AutomationML, the concept of the file itself foresees that in the file we put the data, so for instance the list of signal, but we need also to provide the semantics of the signal. So we have a definition, hopefully through a role class of the signal concept, its specification, for instance the data type, the range of valid values, and so on. So we have a description of the data along with the value of the data itself. In the target tool, so in RoboStudio, we need to import this information, but of course in RoboStudio the information is stored in a different way compared to the source system. So RoboStudio has to accomplish two main steps. The first one is to read the file and to understand, to recover and understand the semantics of the signals. So the file, the AutomationML, needs to be read, the signal role class needs to be recovered, understand the type of data, the ranges of the values, and so on. So we need to understand the semantics of the data. And then we have to map these semantics against the RoboStudio data structure. So the second step in reading the file is the feeding of the RoboStudio data structure with the information that has been recovered and semantically understood from the AutomationML. So every time we need to use AutomationML file to exchange data between systems, we have to understand that we need an interpreter, which is it's a key phase. We need an interpreter able to map data from the way they are written in the AutomationML file against the data structure of the importing system. Having this in mind, several projects have been devised to use AutomationML as a way to convey data among the phases of a automation pipeline. So for instance, we may have some devices which need to be described and put together, configuring their data in a certain layout which can be again described using AutomationML file. And for instance, in this project of the German government, AutomationML has been used also as a way to convey a self-description of the components of an automation systems. And this is an additional way of using AutomationML. So if the primary role is to convey the data, the second one could be the storage, the description of a certain system. The idea is to have an automation file that includes all the data about a certain device. So if I have, for instance, a motor, I can describe the geometry of the motor, I can describe the power, the characteristics of the speed, of the power, of the couple, of the torque of the system, and so on. The coupling, the mechanical coupling, the electrical connection, and so on. And also all this data could be put together in AutomationML file, since we have seen that AutomationML is able to convey all this data. So if the AutomationML file is somehow linked to a certain device, it could provide the description, a comprehensive description of the systems from one point of view, but it could be very useful to an automatic way of providing information as such device is employed in a system, it's put in the system as a way to provide information to other device, to other components on how such device could work or needs to work together. So it's a way to put together many provider of devices and system integrators and users of systems. And the idea is, as the name of the project says, secure plug and work. So as long as I plug a new device, its internal description in ML format could provide all the information necessary to plug, to put the system, this device in the system. Here we have a further development of the same concept and an application to a smart conveyor system, flexible smart conveyor system. If we imagine that a conveyor system made of several devices, motors, sensors, actuators, and so on, and each device has its own description in terms and using AutomationML of the characteristics of the device itself, I can imagine to make flexible lines of conveying material. I want to say that the lines are made of modules that contain the descriptions in terms of AutomationML, and they are put together freely, one after another, and then they are able to exchange information and start to work together as soon as they put together, since they have internally of the information required to make them work, all the information that is needed to be exchanged to work together. So there are many usages we can imagine for an AutomationML file. This slide reports some of those. For instance, we can use the AutomationML to exchange data within integrated engineering tool landscapes, which is quite the original usage of AutomationML file. But we can think about AutomationML also in simulation environment. So it could be used to support the generation of a simulation model in virtual commissioning. So when we need to exchange data between and want to commission a system virtually, for instance, we want to test, debug our software code on a machine which is only virtually defined. Or we can use AutomationML to exchange resource structure from integrated engineering environment, also using third parties engineering tools. So it's more or less what we have seen from the previous example. AutomationML becomes a means to store, convey information from one system to another. Or we can also use AutomationML to create an asset model of relevant information also for cloud-based application. So when we have Industry 4.0 scenarios with interconnected systems, AutomationML becomes a way to exchange information also using the cloud. An example of using AutomationML comes from the German company Lenze, which is a company involved with drive and automation technology. They provide several systems for the automation ranging from motors to software system to PLCs, drivers, and so on. And they have a quite complex life cycle of their products, since they need to support the process of definition of a certain automation solution, starting from the planning phase, and so as an help to a potential customer, and then to support the ordering phase of all the equipment which is necessary for a certain system, and then maybe the development of the code of the system, the engineering phase of the system, and then support the commissioning until the operating phase of a certain system. So they decided to incorporate and use automation ML as a way to bring information, to exchange information through the several steps of a automation system process development. So starting from the application idea along the engineering tool change, automation ML is a way to describe the machine, but also to provide a list of the devices which are needed and convey the information about such devices until we reach the commissioning and also the service, because when we need a maintenance task, automation ML comes again as a way to retrieve information about a certain device. AutomationML finds very nice applications also in European projects. I would like to briefly recall its application in the Integrade UE project. I want to be very short and invite you to listen to the training session provided from the University of Coimbra regarding this type of application. And basically in this project, Automation ML has been used as a way to orchestrate the information through several systems in the engineering pipeline. So as a way of assets data modeling, data exchange, but also as a way to convey the offline programming information. And the application is a VAM process, additive manufacturing process, welding process, where you need to describe the system, which is made of rotating table, the robot, welding gun, and so on. But we have also a part to be realized, so we need to represent the geometry of the part, and we also need to represent the process, which is the path, the deposition path of the metal to build the part. So there are many software tools involved in this tool chain, and we have the CAD design of the parts, so the geometry of the part to be realized. We have the elaboration of the deposition paths. We need to simulate the geometry, the behavior of the part of the metal being deposited and the distortions, and possibly update the geometry or the path planning. So all this information are quite heterogeneous, and Automation ML comes to help this process as a way to exchange this type of data among the different software tools that may be employed to this aim, until reaching the simulation of the deposition process in a robot virtual simulation environment, and finally command the robot to execute the part. And in the project, Automation ML and a special customization of Automation ML called PathML has been defined to convey all this type of data. And many plugins has been developed to make all those software tools exchange the data in PathML format. And those tools include robot programming, so RoboDK, RoboStudio, and so on, but also multi-physics simulation, as in the AC tools, or geometry or paths visualizer using FreeCAD, for instance. And a special software, a special interface has been defined to generate the original ML file, which then is exchanged between the systems. And as you can see, the interface of the file contains many specific attributes about the process itself, going from the layer parameters to the process parameters, welding characteristics, and so on. And this software is also freely available at Zenodo and can be downloaded and exploited to develop your own application. And it's a very nice and good representation usage of AutomationML as a way of exchanging this heterogeneous information against between very different systems. In fact, in the project, many different software tools and combination and test cases has been developed, as you may see here on the right, and you see very different type of geometries being designed by different software tools and elaborated and or simulated with different software tools. And AutomationML basically succeeded to exchange data among such set of different software tools. Also in the PeneloPe project, the AutomationML has been widely used in several applications. I would mention a first application from our side, from UNIMORE, where we used AutomationML, as mentioned before, as a way to represent our demo cell performing an experiment regarding the robot accuracy increase thanks to the usage of a laser tracker to measure the position of the robot and correct it on the fly. And as mentioned before, we have used in this case the AutomationML editor as a tool to represent our cell in terms of the equipment, the process, and the process control systems. So a usage of AutomationML in a very standard way as a representation tool, but also a description of the devices of the cell, but also as a way to convey the process parameters to be exchanged with a digital thread or an external systems that can interact with any user. So the user can change some parameters of the experiment, which then feed back to the cell and to run again the experiment under different conditions. Another nice usage of AutomationML has been done by the PeneloPe partner Biba. I invite you also in this case to follow the training session devoted to this application where they provided all the details and a practical example of usage of the tool, which is called Telegon, which is a tool able to generate AutomationML file by interfacing Inventor, the CAD system Inventor, and RoboDK to generate in a virtual environment a manufacturing scenario of pipe fittings. And the system is able to read from the CAD data about a certain piece of pipe and describe its characteristic, generate a manufacturing cycle, and then exchange this information to other systems, also using OPC UA capabilities of the software of exchanging, connecting devices and exchanging information. And finally, an important part of the PeneloPe project was devoted to the creation of a digital thread able to describe the different stages of a product life cycle in terms of the process of definition, including design data, material data, but also all the data regarding the process itself, simulation, tolerancing, software tools being used in the process. And to support and to store all this information, AutomationML was chosen as a primary choice, was most suited format to have a comprehensive description of all these characteristics. We see in the slide on the right hand side an extract of an automation file which is generated by a portal which has been developed to create this sort of file, including all the information regarding a certain process divided in operation, characterizing each operation by the type of task being accomplished, but also by the input files necessary for the operation or the software files, which are software tools which are used to accomplish the operation. Don't think only on manual tasks, but also to simulation or design activities in general. And you see here you have a nice description made in AutomationML where we have three main sections, which are the file section, so the list of all the files which are generated in, or used in the process. Then we have the list of operation, which is basically the description of the process. And then we have the software being used. And these line blues are the connection between all these elements. See, this kind of connection are possible in AutomationML file and helps to connect a certain file to the operation where it's used to the software system that has generated the file itself. I'm going to present you AutomationML Hub. AutomationML Hub it's a software we are developing at UNIMORE, and it's part of our work on automation ML. And I will present you the main idea of the software and its application to flexible building test case. Automation ML Hub wants to be a software that to generate and exchange among different systems ML files. I think that the key word is hub. Hub because the software wants to be a sort of exchanging node, an exchange hub based on automation ML between several software systems which are used in the context of automation and robotic systems. So the idea is to have a software when we can open an ML file and where we can edit data about an automation ML. I refer to from general project data until the modeling of the resources, their geometry, so provide a geometric representation of the resources, but also specs and characteristics of the processed part. Of course, we are referring to discrete production, and where we can also define process. And from what we have learned and seen from the previous slides, you can understand that this information is very heterogeneous. So we need to cope with several types of data and try to have a means of representing them all. So that from here comes the idea of having a hub and unique system where geometry, process data, processes can be seen and represented and reviewed and exchanged with other system. And the idea so is to having this environment quite simple to use, or at least intuitive for an automation engineer. So the idea is to simplify the creation of the file, hiding the technicalities of the language. We have seen from the previous slides that we need to know several details about how the XML file is composed, the attributes, the role classes, and so on. We think that this is quite specialistic knowledge that should be hidden in a software system making use of automation ML. So here the idea to have a tool which expose the concept in a usable manner to the final user, but still the system is able to compile to generate an automation files which is complete, rigorous, and respectful of the standards and best practices associated with the file format. In this way, the tool can be seen as a way to import information from several software systems and above all, provide all the data that can be then used to feed physical environments. For instance, a robotic cell, we can see down here, and of course provide the data to the controlling systems of a robotic cell like this. So for instance, provide the code to move the robots or the code to run the PLC system coordinating the cell. But the same information should be go in virtual prototyping environment, for instance, RoboDK or RoboStudio by ABB, to run virtual simulations of the physical environment, or possibly running them together, realizing the concept of the digital twin associated to a physical environment. In order to make the concept more clear, I would like to present you two applications. The first one is the manual definition of a flexible milling process. Our cell is made of a cooker robot and a spindle and a tool storage with some tools to be mounted to in the spindle in order to perform simple milling operations, deburring processes, and so on. So the idea is to use AutomationML Lab to have a way to describe this setup, describe a product to be processed, and above all, to describe the process, the operations, the tasks we want the cell to perform. So we developed the functionalities to describe all this data, all this information in the AutomationML Lab to be then stored in an ML file. So the idea is to represent the whole system adopting the product process resource pattern, the well-known pattern, in order to accomplish all the information connected to the automation system, to represent the geometry of the devices present in the cell and used for the application, leveraging, of course, the Collada format. We want to use a rigorous semantics. Our choice was to review all the white papers and best practices which have been collected by the ML organization. We put all them together in a systematic way. We completed a database of all the role classes we have encountered, and we store them in AutomationML software in order to use them as main reference, as principal reference to build our representation of the milling setup. In this way, we believe that the standardization of in using a certain naming for the roles and certain role libraries is fostered, and the usage of AutomationML can grow on a stronger basis. And then we represent the process we want to make as a sequence of basic milling operation. Each operation has been attributed with the code of the robots to drive the robots to perform a certain action. In this way, at the end of the milling sequence, the system is able to generate the whole code to drive the cell, and this code can be used to run to feed the robot controller and then to run the cycle which has been defined. Then I will show you a video to highlight how the process is accomplished. As a second example, I would like to show you a more automatic definition process. Here the idea is to perform a special milling process, which is a debarring of a casting cover. So as you see here in the picture, you have a casting piece where some bars due to the process appears, and we want to use an automatic debarring process where the robot takes the part and offer the parts in front of the spindle to remove certain bars. And we want this process to be flexible. Flexible because bars may appear in certain location or not, or they may appear in different sites. That means that I could need to process a certain edge or not. I could need to process a certain bar with different tools according to the size of the bar. And also the extension of the bars may require one or more passes. So what we want to do is to recover the cell definition from the previous example. And then we have defined a reconfigurable milling cycle in which the user just defines the bars he wants to process and the sizes of the bars. And then the system elaborates an optimal cycle and describes it in terms of AutomationML file. So the AutomationML file that can then be used to be processed in the physical environment or in a virtual environment for some commissioning testing activities. Of course, the definition of the bars to be processed is it's manual so far, but in the future the system could be still more flexible if some measurement systems is adopted to make the system able to understand automatically where are the bars and their size and how to be processed. Also in this case, I have a video to show the workflow in the software to generate two alternative cases of process according to the bars and the relative size which has been chosen by the user. Finally, I would like to present you a final case, which is the connection that has been implemented in the PeneloPe project between the definition of a process in the PeneloPe digital thread and how this process is then brought to the physical assets through ML. In particular, I will show the work we have done in the SAMXL Fokker Aerospace pilot line. As mentioned before, the tool developed by the Atos partner of the project allows to define a process made of operations inside a portal, inside a web portal, where through a graphic interface a user can define some blocks representing the main steps of a process and then add specification to this main process, adding subtasks and files and software linked to each step. This information can be saved in AutomationML format we have described before, and through some APIs, it is possible to download the file, making it available to a controller of a system, which can be physical systems like the physical pilot line in SAMXL, or could be also a virtual model of the same system developed in a virtual environment. In particular, in the context of the Fokker pilot line, the AutomationML feed a ROS2 coordinator. ROS2 is a platform able to coordinate robotic systems. I will show you how the AutomationML is used to give instruction to the ROS2 environment, and then the same environment can move the physical devices, which are robots, cobots, gantry system, in the SAMXL environment, but the same coordination system has been used also to move a virtual model in RoboDK of the same assets. So both the physical and virtual process are fed by the same digital model, and AutomationML is the means to convey the information defined in the virtual digital thread until the physical assets. Basically, these are the main steps of the process. At the beginning, the process sequence is defined in the Atos digital thread front end, and then the AutomationML file is generated from this definition and downloaded. Then we need to bring the AutomationML definition into the ROS2 environment. Here we have decided to convert the ML file to interpret the ML file by a Python script and convert it in a much simpler XML file containing the sequence of the operations to be triggered. This was just an implementation choice. And all these first 4 steps are explained in this video that I will show you in a few minutes. And then once we have the XML with the main steps of the process provided to the ROS2 coordinator, the process can start. And I can show you the process, how it is simulated in the RoboDK environment. So you can see from the next few slides and videos how the process defined in a digital thread goes through the steps until the simulation in RoboDK. Just a few words to make the videos more understandable and clear. The virtual simulation is controlled by ROS2. ROS2 has a quite sophisticated mechanism made of nodes. In particular, they speak about action clients and action servers that exchange data. So we have a client sending some requests which are received by the server. The server commands the simulation and provides back the feedbacks to the client. And this mechanism allows to control the system in an interactive way in a nice manner. The action client received instruction from an XML file containing the sequence of action one wants to perform. So the first step was to describe the process we want to accomplish. This slide contains some of the elaborations that has been done to define the process that we wanted to demonstrate in the Fokker pilot line. Basically, few steps have been included, which is the positioning of the skin of the fuselage of the plane, and then the positioning of the stringers, then the welding of the stringers, and the control with the non-destructive test of the welding process, and some operations at the end around the cargo door. This information has been standardized and codified according to the attributes and the fields available in the Atos digital thread in order to be described, including all the information that is necessary to the ROS2 coordinator to trigger the simulation process or even the physical one. So you see here that we have the module assembly, in which we have the operation skin thickness measurement that triggers a gantry procedure which moves the entity scanning of the skin, and so on, with the positioning of the stringers, the welding on the stringers, and so on. Here I've presented some few screenshots about how the process is instantiated in the Atos tool. Here we see the 5 main modules of the product that basically are assembly, welding, or non-destructive test modules. In each module we have an operation that better describes the module itself. We have used the operation name as a field able to convey the type of operation. That could be gantry procedure if the operation involves the displacement of the gantry, or cobot procedure if it requires the usage of the cobot. And then we have used the comment field to describe what specific type of operation we want to perform. So we have used the fields and the information that a user can input in the Atos tool to convey all the information that are then required by the simulation of the process. Then this information goes through the AutomationML file, is exported from the Atos tool, and then is processed by a script, a Python script. You know that ROS2 can be enriched with scripts, with Python scripts. So the AutomationML file that consists of many tags and a quite complex structure, as we have seen before, can be simplified in order to generate a much easier intermediate file that is then actually used by ROS2 to drive the process. So it's a simplification process just for practical purposes. And here you see that the file simply contains the list of the procedures to be activated. So entity scanning, then pick up place stringers, and then welding stringers, and so on. And these operations are triggered by the coordinator inside the ROS2 in order to activate the action client, the action server, to actually perform the simulation. And here you see some details of the conversion process that can be done with the script developed by UNIMORE in Python that parses, interpret the ML file and convert it in the XML file used by ROS2. And here now I can show you a first video that provides you all the details of this first part of the steps going from the definition of the process in the Atos digital thread until the creation of the XML file. Now, in this second part of the process, the single step of simulation has been defined in the RoboDK environment. For instance, we see here the how the scanning of the skin has been commanded, and here follows the definition of the pick and place of the stringers on the of the skin. This process has been repeated for all the operation. So we also included the process, the simulation process of the welding of the strings after their positioning. And finally, also the operations linked to the drilling of fasteners around the cargo door. In this case, a cobot mounted on a movable platform has been employed. Then, having these part single operations, these operations are coordinated by the ROS2 according to the sequence defined in the XML file we have seen before. The final simulation is shown in this video. The mechanism described so far has been used to optimize the process. So evaluating in a virtual environment the sequence of operation and above all different sequence of operation and subtasks, we were able to understand what is the best sequence of tasks to reduce the time of accomplishing the whole process. And after a few tries, we were able to reduce the cycle time and, of course, the total travel length of the gantry systems, which is the main source of time spent, time required to accomplish the cycles. So the presented usage of the system and its connection to a easy system to define the cycle and its connection through AutomationML file becomes a powerful way to optimize the simulation and then use this optimized cycle to drive the physical assets. So that concludes this training session of fundamentals of automation ML. I hope you find this presentation interesting and that I was able to give you the main highlights, the main characteristics of the language, and above all, I hope that you understood what are the main possibilities offered by this language, possible application, and how we have used it in our projects inside the UNIMORE and how it was used in the PeneloPe project to realize a integration of our pipelines with the digital thread. If you have any additional questions, curiosity, comments, please feel free to reach me. Thanks you again for watching.